Okay, we went through the Nyquist plot and Nyquist criteria and how to calculate everything. Now let's just start doing examples from start to finish. So let's say this is our configuration. Let's go through the Nyquist thing. The loop transfer function is just this guy times this guy. So that's just the unity feedback. That's a 1 there. So here's the transfer function. It has poles in the left half plane, but it has a 0 in the right half. So this is a non-minimum phase system. We couldn't have done a Bode plot for this, but we can do Nyquist. And we let MATLAB draw the Nyquist plot. And let's see here, that's a -1 there. That means any point on here, or that this point corresponds to -1 over k, or k equals 1. This point looks to be at about 0.5. So -1 over k equals 0.5. So k here equals -2. We needed the p. That's how many poles in the right half plane of the loop transfer function, this product, and there were no such poles. So p equals 0. So now we need to calculate n, the number of surroundings of the Nyquist loops. Because p, the number of poles of the closed loop system in the right half plane, equals n plus p. That's the Nyquist criteria, the Nyquist formula. So let's look at this guy. By the way, this guy has no infinite loops. It doesn't, the loop transfer function had no poles at the origin. Out to the left of this point, there's no loop, so n equals 0. Any point in here, pick a ray out to infinity, 1 crossing in the clockwise direction, n equals 1. Follow this around. This guy is still going clockwise. Pick a point here, out to infinity. There's 1 clockwise crossing, 2 clockwise crossings, n equals 2. Then to the right of this point, n equals 0 again. I work left to right. So let's see, out here, that's where the -1 over k is less than -1. Do the inequality algebra, that means k is between 0 and 1. There z equals, well, in every case, p equals 0. So n plus the p equals 0 in all these cases. We've got 1, 2, 3, 4 segments of the real line to deal with. In this one, I'm out here, n was 0. So 0 plus 0 is 0. No right half plane poles. It's stable for those k's. K is between 0 and 1. The next segment is here. That's for any point that's between -1 and 0. And that means where k is greater than 1. K itself is greater than 1. N was 1. Closed loop system has 1 pole in the right half plane. Out here, any -1 over k is between 0 and 0.5. That means k is less than -2. And there, z equals 2, n plus p, 2. 2 poles in the right hand. And out here to the right of that point, n equals 0. It's back to a stable system. K is between -2 and 0. Put all that together, and here's the z, or how many closed loop poles of the closed loop system for different values of k. I think I can do one more example in this video. This guy. Here we have a pole at the origin, so we've got to deal with an infinite magnitude loop. Talked about in a previous video. This is a cubic, so we'll use MATLAB to find the roots. we don't find the roots of cubics. But it has, let's see, a complex pair of poles in the right half plane. This pole's a real pole in the left half plane. He's good. So E equals 2 in this case. Let's see. Before I draw it, let's think about this. That's one pole at the origin. So I'm going to have a half circle, or 1 times 180 degrees. It's going to go in the clockwise direction, always clockwise. And it follows the direction consistent with the finite part of the Nyquist plot. So it's going to come out of here because I'm following this arrow. Once it goes off, it's going to start going clockwise, 180 degrees, and come back in here. It's going to look like this. And you could, MATLAB doesn't draw arrows everywhere, so you kind of know what's going on. You need to follow it around. Put some more arrows on. So out here, n equals 0. Don't worry about up here. You'll have canceling. They'll cancel. So pick a ray here and go over here. Keep it simple. No crossings. N equals 0. Once you get to here, let's see. I've got counterclockwise a -1, another counterclockwise -2, then a clockwise, so I'm back to -1. I have 2 negatives and 1 positive. On net, n equals -1. Got that? The sign is by whether it's clockwise or counterclockwise, and you add them all up to get the net n. Out here, pick a point there, go off to infinity, just 1 crossing, n equals 1. I won't go through this inequality algebra, but for every case, I have, let's see, 1, 2, 3 segments of the real line to worry about in this problem. Oops. And to the left of the origin, between here and there, which looks like it's a 3. So k equals -1/3. -1 over k equals 3. K equals 1/3 at this point, -1/3 at this point. Then to the right of that. Anyway, this thing is always unstable no matter what k is, but it has different numbers of right half plane poles. So that's our first 2 examples, and we'll keep doing more examples in subsequent videos.